I mean, he gave a great talk, and then the protest showed up.
May I start?
Okay, so now Sergey will finish.
Okay. Welcome back to device simulations. Well, in this my talk, I would like to focus on nitride semiconductors and nitride devices. And what is the main difference of nitride semiconductors producing some problems in device simulations? The first of all is that nitride semiconductors belong to hexagonal crystal symmetry. And this produces some anisotropy in the optical properties and in the dielectric constant. The second issue is that the difference in the energy gap is huge, from 0.7 to 6.2 electron volts. And this means that if we consider the heterostructure, the band offsets between different layers are very, very large. And this produces a very strong impact on the transport of the carriers across the any nitride structure. And also, we should mention the large lattice constant mismatch between different materials, and this means that strain is the issue in the case of nitride devices. Also, there is a strong composition fluctuation, for instance, in indium gallium nitride materials, and this results in carrier localization, and this affects the combination of carriers in the devices. So let's start to consider all the features related to nitride materials. First of all, let's go to the Poisson equation. The Poisson equation should be modified because in the case of nitride materials, first we need to take into account the anisotropy related to the selected hexagonal axis of the crystal, and first we should take into account the reverse piezoelectric effect. Namely, the electric field, strong electric field available in nitride semiconductors produces strain in the heterostructure, and strain produces the piezoelectric charges that modify the electric potential distribution in the structure. As a result, we should operate not with the static dielectric constant, but with the effective dielectric constant, which takes into account the reverse piezoelectric effects. To what extent is this important? Here is some examples of calculation of the dependence of dielectric constant component of the tensor as a function of the inclination angle of the hexagonal axis. So here is the inclination angle. In principle, we can obtain the heterostructure with the normal hexagonal axis and inclined at every arbitrary angle. And what we see here is the behavior of the dielectric constant of aluminum nitride as a function of the inclination angle. And you can see the variation is approximately 20% of the whole dielectric constant. It is rather large value. And also, if we calculate the effective dielectric constant, the difference between the static dielectric constant and effective dielectric constant is approximately 15%. So it is also large value and should be taken into account. In the case of gallium nitride, this situation is less anisotropic, but nevertheless we should keep in mind this reverse piezoelectric effect. I'm sorry. The next. In addition to the space charge created by electrons, holes, and ionized acceptor, there is also the electric polarization in nitride semiconductors. The electric polarization consists of the spontaneous electric polarization, which is rather high, and piezoelectric polarization dependent on strain. And you can see here that the charge produced by electric polarization depends on its variation in space. So if we consider the uniform layer made of aluminum gallium nitride, indium gallium nitride, or indium aluminum nitride grown on gallium nitride, you can see here how the polarization charge formed at the abrupt interface can vary with the inclination angle of hexagonal axis. So actually, if we have the normal nitride structure, in this case, every interface produces surface charge related to the discontinuity of the electric polarization. And you can see that we can control the polarization charge by a proper choice of the inclination in nitride heterostructure. Well, to what extent is it important to take into account the real polarization charge? Here you can see the simulated band diagrams of nominally the same single quantum well LED structure with different polarization. This is a typical polarization for practical application. The metal orientation of the crystal. What we can see? First of all, the negative polarization charge at the bottom interface of the quantum well produces some peak, some potential barrier, preventing injection of electrons into the quantum well. The same for holes. And the right side of the heterostructure is pushed down due to electric field existing in the quantum well. The electric field is very strong, and therefore this asymmetry of the quantum well related to the polarization charges is also strong. If we consider the LED structure with the opposite direction of the hexagonal axis, that is the N-nitrogen polar structure. In this case, you can see that the potential barrier before the quantum well is suppressed for holes, the same for holes, and the right side of the structure produces the natural carrier confinement. So this is a big barrier preventing electrons from leakage to the p side of the structure, and the same barrier for holes. Unfortunately, by technological reason, realization of the N-polar LED structure is not possible at the moment. But this is just the best design of the nitride LED structure. And also, this is an example of non-polar structure with the zero polarization charges at the interfaces. You can see here that the electric field in the quantum well is controlled by the pin junction electric field. And this is the example of semipolar structure. So the choice of the inclination angle of the hexagonal axis enables efficient control of the polarization charges at interfaces of the structure. Well, there is one more very helpful properties of the polarization charge. If we consider the nitride alloys with a graded composition, in this case, the polarization produces the bulk space charge in the structure. So if we have, for instance, let's consider the aluminum gallium nitride as an example. If the aluminum content is increasing along the hexagonal axis, in this case, the polarization charge is positive, and some electrons try to come to this region in order to compensate this charge. If the gradient is of opposite sign, in this case, the negative polarization charge is formed in the bulk of the graded composition semiconductors. And this results to accumulation of holes in this region, which is helpful in some particular case. For instance, there is a big problem with deep UV LED structures because in deep UV LED structure operates with the aluminum gallium nitride alloys, and the activation of magnesium acceptor in these alloys is very huge. It exceeds, in the case of aluminum nitride, 300 millielectron volts. This means that if we dope the aluminum gallium nitride with high aluminum composition with magnesium, only small part of magnesium acceptor will be activated. And in reality, we cannot obtain the whole concentration higher than 10 to 16 per square centimeter. And this means that such a concentration is inapplicable for the real devices. What can we do? We can use the polarization doping in this case. This is just the simulation, and this is a prototype of the deep UV LED structure which doesn't contain magnesium acceptors at all. If we consider such a composition, aluminum composition, and grow the structure along the hexagonal axis, what we can see here, this descending composition gradient in this contact in this layer produces a big amount of holes without impurity doping. So this doesn't mean that the polarization doping by itself produces holes. This means that polarization doping produces the space charge which accumulates the holes, attracts the holes from other part of the structure. But what we can see here, the concentration of holes is about 10 to 19. Such a concentration can never be obtained by impurity doping in such semiconductor structure. So in this case, polarization is very helpful, and it produces some opportunities for design of, for instance, deep UV LEDs. As a result, the operation current of such LEDs is very close to the ideal operation current related to the band gap of semiconductors. Well, but this not only the advantages of polarization doping. There are some disadvantages. And let's consider some problem related to simulation of nitride semiconductors. Let's consider the LED structure operating at the green spectral range. It consists of 5 quantum wells with the indium gallium nitride quantum wells, approximately 25% of indium. And what we can see, first, which we can see, is the step-like alignment of the band diagram. So also the quasi-Fermi level produce the step-like behavior. And this is the reason of the overestimated operation voltage of the devices. If we go to the origin of this overestimation, we can see that this drop of the quasi-Fermi level is accompanied by a reduction of the concentration of electrons at this side of the quantum well and holes at the opposite side of the quantum well. Actually, we see a formation of very insulating layers near the quantum well interfaces. And if we apply the drift-diffusion model, it always should produce the overestimation of the operating current. The reason is that we neglect the transport mechanism specific for dielectrics. And what are the mechanisms? Tunneling, trap-assisted tunneling, and also we should take into account that the height of the barrier depends on the composition of the quantum well. And fluctuations of the composition results in fluctuation of the barrier height. And this also is not taken into account in this model. What can we do with this? try to take into account the quantum mechanics. And for this purpose, there is approach which take into account that electrons is not a classical particles. It is delocalized in space. And actually, the electrons start to feel not only the potential energy in a particular point, but in the surrounding region too. And there are many theories introducing the so-called quantum potential. There is some differential formulation. This is a well-known Bohm potential, Wigner potential, and Wigner-Kirkwood expansion. All of this formulation operates with a second derivation of either carrier concentration or the lattice potential. And this is very inconvenient for simulation because what to do at the interfaces between semiconductors where the carrier concentration and the potential exhibit discontinuity. So this problem is not resolved up to now, but fortunately there is some integral formulation where the effective potential is introduced, which is the sum of the initial lattice potential and quantum potential. And in this case, the effective potential is defined as the convolution of the real potential, effective mass potential of the structure and some core. And what is also interesting, you can see here very different forms of the quantum potential. As for the effective potential, there are very different forms of the core producing the effective potential. All these quantum mechanical corrections operate with some space scale, which is just related to the de Broglie wavelengths of the carriers. But there is some numerical constant, gamma factor, and gamma factor depends on the particular form of the effective potential. And it is related to different approaches, excuse me, a different assumption used in derivation of these quantum corrections.
So can I ask you a quick question?
Yeah.
From the integral formula,
Yeah.
What I'm reading is this is just UQ. Where is the plus UC part?
Where,
If your UQ is the Laplacian?
here it is.
Right, but when you are writing the integral,
Okay.
if I hit it with the Laplacian, I'll just get UQ, right?
OQ, this is the quantum potential. Actually, when we speak about the effective potential, it doesn't distinguish the initial potential and quantum potential of such a kind. It operates with the sum of this potential. And actually, it is the convolution of the
I'm confused between differential formulation and integral formulation. You are basically integrating the last line here. So there is a Wigner-Kirkwood expansion, and then you are integrating it and you are getting that line, which would give UQ in my book.
I'm not sure that it's possible because that is a derivation in space, and this core sometimes includes the momentum space. So it depends.
So G is not what I'm thinking.
How are they obtained? They take the rigorous quantum mechanical transport equations, like Bloch equation, like density matrix equation, and using some assumption, obtain the quantum correction like this effective potential. But again, depending on derivation, depending on the assumption, we have the gamma factor, which varies from this value. Here is P. Actually, this factor can can produce the uncertainty of the order of 10. And this is important. What people suggest to overcome this uncertainty? They suggest to use the gamma factor as the fitting parameters and to fit the effective potential to particular problems. I would like to show you how we have optimized the gamma parameter. We consider the superlattice consisted of indium gallium nitride and gallium nitride. Here is the initial potential accounting for the polarization charges. And here is the effective potential, producing much more smoother potential relief in the structure. And what is interesting, the bottom of this effective potential corresponds to the energy level of confined states in the quantum wells. The situation for holes is not so good because they are different from the position of the top of the valence band. What we have from the point of view of prediction of carrier concentration. Here, the solid line is the results of Schrödinger exact solution of the Schrödinger equation. And, okay, it is not seen here. There is some quasi-classical distribution of the carrier concentration, which are very unlikely to this distribution. And this curve is the results of the effective potential calculations. In the case of holes, they corresponds very well, and here is some difference in the position of the minimum of the concentration. And one more test. We have calculated the current in the case of the barrier, triangular barrier with the base D and H. And we have calculated the thermionic current accounting for the carriers that overcome the barrier, and tunneling current and total current. And here you can see the comparison of the direct simulation of the tunneling through such a barrier and plus thermionic current, and the results obtained by effective potential. So you can see that if we don't consider low temperatures and if we don't consider very high height of the barriers, there is a good corresponding, and this corresponds to the gamma factor equal to 0.7. Well,
What is the quantum potential?
Quantum potential is dash dot line. Solid line is the exact solution of Schrödinger equation.
And the shaded blue is the true potential?
Blue is electrons, red are holes.
What is the quantum? What is your modification to you're showing the conduction band and valence band profiles.
Yeah.
What is the potential? I'm sorry.
The effective potential.
Yeah.
Here it is.
Okay. So
Here it is. It is smooth.
In which one are you showing there of your four?
And?
You had a list of effective potentials on the previous slide?
Yeah, we calculate the effective potential and the carrier concentration corresponding to the effective potential. So
Okay.
this is just the carrier concentration. Well, okay.
For quantum case, do you have to do it self-consistently? That your potential depends on the density, right? On the electron density, so you have to do it self-consistently.
Yes, right. And what does it help us to understand, to improve the predictability of the drift-diffusion model? If we introduce the quantum potential into drift-diffusion model, we obtained much more flat alignment of the band gaps in these LED structures, and instead of the operation voltage of 5.5, we get the operation voltage of about 3.5. It is still higher than the experimental data lying near the 3 volts. But what is important, we take into account only the quantum corrections to the real potential. We didn't take into account the fluctuations of the barrier height and so on. So quantum potential, the effective potential framework enables, in principle, to take into account and this effect too. And this is advantages of using the quantum potential. Well, and what are the disadvantages? First, there is still an uncertainty in the choice of the gamma factor. Because in literature, people say that gamma factor is different, for instance, for quantum wells and for the delocalized states. This is one issue. Another issue is that quantum and effective potential is initially developed for the unipolar devices. First of all, for transistors and so on. There is no recombination of carriers and electrons and holes. So if we use the effective potential, we need to reconsider all the recombination issues. And this is not yet done up to now. And finally, in principle, the effective potential can be used in two-dimensional simulations and three-dimensional simulations. In the case of one-dimensional simulations, the increasing of computational time is by a factor of 1.5, maybe 2. In two-dimensional and three-dimensional simulation, it is expected that there will be much longer computational time. But nevertheless, it is very promising for the three-dimensional computation too. Well, let me go very shortly through the efficiency of the LED. Here I have listed different efficiencies which are mentioned in literature. First of all, we can introduce the recombination current in the whole structure, the recombination current in the active region, and radiative recombination current in the active region. And in this case, we can calculate the leakage, which is the difference between the total current flowing through devices and total recombination current. We can introduce the injection efficiency by this ratio, and radiation efficiency. And also, which is especially important, is internal quantum efficiency of LED, which is the product of the injection and radiation efficiency. If we consider the optical power emitted by LED, we can introduce the external quantum efficiency. And the ratio of external quantum efficiency and internal quantum efficiency produces the light extraction efficiency. This means the portion of light which is emitted by active region, which was outgoing from the devices. And let's consider again the red LED structure. If we calculate the internal quantum efficiency, we see the dome-like dependence. It's easy to understand the increasing part of this curve, because if we increase the current density, the carrier concentration increases, the radiative recombination becomes stronger than non-radiative, and we see the increasing of the internal quantum efficiency. But what is the reason of the efficiency drop at high current here? If we calculate the injection efficiency means the part of the carriers that come to the quantum well and recombine there. The injection efficiency drops down nearly at the same current density where the drop of the efficiency is observed. And the reason is the leakage of the electrons from the active region to the p side of the LED structure. This is the fundamental limitations, because if we consider the aluminum, gallium, indium phosphide materials from which the red LEDs are made, in this case, the conduction band of SET is limited by the crossover between the position of the conduction band in the gamma valley and X valley. This is a non-direct band gap of the semiconductors. This point chosen for the active region corresponds to the wavelength of 650 nanometers red emission. If we want to get a shorter emission wavelength, we should introduce aluminum in the active region. And in this case, the band offset becomes lower and lower, and efficiency drops down when we go to the orange range of the spectrum. I would like to pay your attention on the typical concentrations of carriers in the red LEDs. They don't exceed 10 to 18 per square centimeter. If we consider the LED...
Go back to so you should tell us what is the voltage, what is the bias when you reach 100 amps per square centimeter.
You mean the voltage?
Yes.
Operation voltage.
So
Oh.
it means that in that case, you bias so strongly that you can transfer.
Yeah, it is very close to the... It depends on the current density. And the current density of exceeding 10 amps per square centimeter, it is very close to energy gap. So
That's why you have it.
yes, right. Well, let's go to nitride semiconductors. This is a typical nitride LED structure. The first we see is that the carrier concentration is higher, much higher than 10 to 19. And this results from the large band gaps, large conduction and valence bands offsets. This results from lower mobility of the carriers and so on. If we consider the internal quantum efficiency, you see very similar behavior, very similar to the red semiconductors. However, the nature is quite different because high electron concentration involves interplane the Auger combination. Auger combination is non-radiative process which needs a high carrier concentration in the active region. So actually, at this part of the curve, we see the dominating radiative recombination, and in this part, the Auger combination comes to play, and it decreases the internal quantum efficiency of the LED. Well, when we speak about the efficiency, we should to discuss the recombination coefficient. And the most simple way is to discuss the recombination coefficient of radiative recombination. Actually, the way of calculation, okay, 2 minutes, is very straightforward. We should calculate the wave functions in the LED structure, overlap integral, and use the momentum conservation law in the radiative recombination, and to make summation of over all the momentums involved in the transitions. This produces such a curves from the quantum wells of different thicknesses. And from the first insight, there is very good correspondence by the value of the radiation recombination coefficient. By the slope is very different. And if we consider the Auger recombination, I will skip some history preceding this history related to the determination of Auger recombination coefficient. In this case, we can see that conventional theories suggested by Manas Kiopaskis and Chris van der Walle, they obtained the values very similar to the experimental data, but the slope is different also. So, in my opinion, this is related to the carrier localization. I have no minutes.
Roughly no minutes.
No minutes. Oh, at this very interesting point, I should to finish my presentation, because actually, if we consider the carrier localization nitride semiconductors, there are many evidences for the deep localization of holes. Deep localization of holes that affects the recombination coefficient, and this is a very interesting issue for the further discussion. I'm sorry.
Okay, we're in negative time here. So you really have to ask a question, start over here and go back.
One question concerning the effective potential. It reminds me the philosophy of the landscape potential, because you introduce some quantum effects in the effective potential. Except that I could not see the origin in terms of mathematics of the potential that you have. There are different formulas, but what is the motivation for using one compared to another? This is what I missed.
Okay, the motivation originates from the drawback of the drift-diffusion model, that the drift-diffusion model for nitride semiconductors cannot predict correctly the operation voltage of the LEDs. If we go to the other experiments, there are very interesting experiments carried out in the UCSB for the unipolar conductivity through the multi-quantum well, aluminum gallium nitride multi-quantum well. It doesn't produce the Schottky-like behavior despite of the South-like behavior of the potential relief. So there are many different points which show that the transport in nitride structures should include some quantum mechanics.
No, that's clear. The point is that the justification for using one formula or another.
Yes. What we have done, we take the effective potential suggested by Dragica Vasilevska from the Arizona State University. They used the rigorous quantum mechanical transport equations.
No, we have a session for discussion tomorrow. So we have time
Oh.
and we have much more time to discuss this tomorrow. It's a big question.
It's a huge question.
Yes.
Yeah.
So we cannot take it in 5 minutes.
So till tomorrow.
Yes.
Good.
Continue tomorrow.
Okay.
Okay, I guess we.
Almost everyone has something to say.
Does it mean that I can continue tomorrow with the recombination coefficient?
I think the big question is, not asking questions, is your use of effective potentials and the physical, well, my question tomorrow will be the physical justification for this.
Physical justification.
Yeah, are these just ad hoc, or do you have physics behind it?
That was the question, so let's
No, for
put this
tomorrow.
off
For
for
tomorrow.
tomorrow. And also,
Yes.
dinner tonight, you're allowed to try to resolve
No,
something.
that's not,
In this case, I should touch the history
it
of
should be
the.
for the whole group.
Yes.
Well, you can tell us what you resolved, if you resolved.
No, it should be.
Okay, our next speaker is Marcel Filot.
Thank you.
Marcel, you have another 15 minutes. Remember that. We have another